So what we're going to talk about now are trig equations. And realistically, there's no one set method for these. All of the problems are unique. So it's just going to take a lot of practice to try things out. But your whole goal is likely going to be find theta values that make the equation true. The problem with our trig functions is we have that cyclicalness. So we have cosine of theta equaling some number for an infinite number of values. So it depends on the problem whether you need to select values within a range or if you just need to find all of the solutions, okay? So a lot of times you're going to end up having to break this down into simpler equations and figuring out, okay, when does sine of theta equal 1/2? And then you'll worry about those boundary restrictions on theta. You might need to do some methods and have to factor. So kind of like when we were going through and solving or verifying trig identities, you might have to do some manipulations to make it into an equation you know how to solve, and then go back to your substitution and see what does then my theta have to equal, okay? So we're going to try a ton of different examples. We'll start with something relatively nice. We're going to solve cosine of theta minus 1 equals negative 1/2. And our theta is going to be between 0 and 2 pi. It can equal 0, but not 2 pi. So this restricts it to just once around the unit circle. So this one, if I have just a single trig value, I likely want to get it to just be what does cosine of the angle have to equal. So we're going to go ahead and isolate the trig function. And this is asking where does cosine of theta equal 1/2, but specifically on the interval from 0 to 2 pi. So if you think about the cosine function, once around the unit circle, there are two places where cosine is positive. You have an angle up here in quadrant 1, and then you have an angle down here in quadrant 2. Where cosine of theta is 1/2 tells you it's going to be a 60-degree reference angle. So this angle would be pi over 3. So one of our solutions is pi over 3. But now I need this solution down here, which is going to be going around the unit circle to get to. So in this case, again, you can have your unit circle out. You have to create it on a test though. But this is going back pi over 3 from 2 pi. So that specific angle would be 2 pi minus pi over 3, which is 6 pi over 3 minus pi over 3. So this second angle would be 5 pi over 3. So the second solution where cosine of theta equals 1/2 on the interval from 0 to 2 pi is at pi over 3, okay? So that is our first trig equation, right? So this is what we're hopefully going to boil it down to. Again, things can get more complicated because you might not have just theta on the inside. So we'll see what we have to do in those instances, okay? But let's try this next one. We've got 4 sine squared of theta minus 3 equals 0. And again, I'm going to restrict my theta to be between 0 and 2 pi. Well, this you can treat exactly the same as if you were solving 4x squared minus 3 equals 0. You can try to factor it if you want, but you isolate the variable and take a square root. So we're going to go ahead and we're just going to add 3 to both sides. And that gives us 4 sine squared of theta needs to equal 3. Dividing by 4 gives us sine squared of theta is 3/4. And then here, when I take a square root, I have to remember to put my plus or minus. So that gives me sine of theta is plus or minus the square root of 3 over 4. And then taking the square root of each of those, that gives you square root of 3 on top, 2 in the bottom, okay? So we're essentially solving two equations from this. We're looking for where sine of theta equals positive root 3 over 2. And then we're also trying to find the angles where sine of theta is negative root 3 over 2. And again, just on the unit circle. So for both of these, we'll go ahead and draw that unit circle. So if I think about where the sine function is positive, that is going to be in quadrant 1. And to have sine have an output of root 3 over 2, that tells me it's a pi over 3 angle. So this results in two angles, pi over 3, which is the one up here. And then the second angle in quadrant 2 would be 2 pi over 3. So both of these would solve that equation. If I'm looking where sine of theta is negative root 3 over 2, well, those are going to be those angles instead in quadrant 3 and quadrant 4. This angle here is the same reference angle. So in quadrant 3, that would be 4 pi over 3. And then this happens to be the same one as the prior example. The angle that would make this true in quadrant 4 is 5 pi over 3. So this one results in two solutions. So what that means is our original equation has 4 different solutions on the interval from 0 to 2 pi. It's pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Any of these, if you plug them into that original equation, are going to result in a true state. Okay? All right, this next one gets a little bit more complicated. So I have 2 cosine squared plus cosine minus 1 equals 0. So here I don't have a way to solve just for the trig function because I have both cosine squared and cosine. So this is where we're going to use a method that's called u substitution. We're going to let u be this function cosine of theta, okay? And this will just make it cleaner so I get a quadratic I can actually work with. So 2 cosine squared would represent 2u squared, plus cosine is plus u, and then minus 1 equals 0. So this is just a quadratic equation that I can go about factoring. So to get to 2u squared, you need a 2u and a u. To get to minus 1, you need a negative 1 and a positive 1. So we'll try this. So the first term gives you the 2u squared, which is good. The last term gives you negative 1, which is good. The outer is positive 2u minus u, resulting in positive u in the middle. So to solve this equation, then we set 2u minus 1 equal to 0 and u plus 1 equal to 0. That tells us 2u equals 1. And then dividing by 2 gives us u has to be 1/2. Subtracting 1 over here gives me u is equal to negative 1. Okay. Now at this point you think you're good because you're like, great, I found values. But again, you want to find theta values. This tells you what u has to equal, okay? So I want to go back here. I now know what u is equal to. So if u is 1/2, this is the same thing as saying cosine of theta is 1/2, okay? And there are 2 solutions that make that true. That's exactly our first example. So it's the 2 on the right half of the unit circle with a reference angle of pi over 3. So the 2 angles that make this true are pi over 3 and 5 pi over 3. So these are both solutions to the original equation, the theta values that work. But then I also know that u could equal negative 1, and that solves the equation. But u is cosine of theta. So this is asking, where does cosine of theta equal negative 1? And, well, that happens right here on the negative side of the x-axis. So the only angle that makes that true between 0 and 2 pi is pi. Okay? So any 3 of these angle values will solve the equation. So again, by making what's called a u substitution, it's just cleaner to work with. But if you feel confident that you can go ahead and factor this immediately, it's the same process. To get the first pieces to multiply to 2 cosine squared, you have 2 cosine of theta and a cosine of theta. To get the last terms to multiply to negative 1, same idea. You need a negative 1 and a positive 1. And then you check, the outer term is 2 cosine of theta minus cosine of theta gives you the right inner term. So then you would set each of these equal to 0 and solve, and you'd end up with exactly the same thing, okay? So if you feel confident factoring with those trig functions in there, go for it. Otherwise, just make this u substitution and it'll be a little bit easier. Okay. Let's try some other types of examples now. Let's solve this equation where theta is any real number, okay? So because of this, if I made that restriction in the last case, or if I didn't have this, theta could be anything. This basically just gives me a starting point, okay? So this angle works, but so does any time I land back on that. So if I go forward or backward a revolution. So here, because there are no restrictions on theta, we can have an infinite number of solutions. It's possible that there is no solution, but if something is going to work, then anytime I land at that spot on the unit circle, it will also work. So here you want to remember that if you add or subtract multiples of 2 pi, this lands you on the same spot of the unit circle. Okay. So that's how we're going to be able to find all of the solutions. So I'm going to start by solving my equation, and we'll worry about all of the solutions afterwards. So again, I'd like to make a substitution. We'll let u be cosine of theta. So that gives us 2u squared plus 3u plus 1 needs to equal 0. Okay. So going through, now I want to factor this. Only way we can get that is 2u and a u. To get the plus 1, everything is positive. You can check the outer and inner work. But this ultimately gives you 2 solutions for u. 2u plus 1 equals 0, or u plus 1 equals 0. So this tells us 2u is -1, or u is -1/2. And here subtracting 1 tells you u is -1. So again, this gives me u, but my u is cosine of theta. So this is the same thing as saying cosine of theta is -1/2. So I'm going to start by finding my 2 key values where that's true. So for cosine to be negative, we would have to be on the left half of the unit circle. These are going to be those pi/3 reference angles again. So this angle up here would be 2 pi/3, and this angle down here would be 4 pi/3. So I get one solution. Theta could equal 2 pi/3. And then I get another solution, theta could equal 4 pi/3. Okay. But now I want to account for, as long as I land in this spot on the unit circle, my output for cosine will be -1/2. So I can add 1 revolution to 2 pi. I can do it again, and then I can keep doing that over and over and over. You can also go backwards 2 pi and go backwards again. So remember, the way we represent those 2 pi revolutions is you can add any multiple of 2 pi, okay? And same thing here, as long as I land 360 degrees, I'll get, or as long as I go around 360 degrees or multiple of that, I'll land in the same spot on the unit circle. So this is where this n is an integer. It's just representing the number of times you go around the circle. And if it's negative, that tells you you're taking those backwards revolutions. Okay. To solve the next one, this would be saying that cosine of theta is equal to -1. And again, I want to find the key angles that happens for. But in this case, there's only a single angle, which is pi. So that is the main angle. But again, if I go around a revolution of 2 pi, that lands me in the same spot. Go another revolution, it lands in the same spot. So I add that multiple of 2 pi. So this n is an integer. So that represents every single possible solution for this equation. Because again, there is an infinite number of places where cosine of theta is -1. There is an infinite number of places where cosine of theta is -1/2. And they will all solve this original equation. Let's try another example. This one's a little more complicated because I have sine squared and I have cosine. But again, I have my theta can be any real number. So the problem with this one is you have two different trig functions. So what I'd always recommend doing when you have especially a sine squared and then a different singular function, write everything in terms of one of them. It's much easier to rewrite sine squared than it is to rewrite cosine. So here we're going to rewrite this equation using cosines. So this is where that Pythagorean identity comes into play, because we know sine squared of theta plus cosine squared of theta is equal to 1. So I can write sine squared easily in terms of the cosine function. Okay. So instead of having sine squared of theta equaling 6 times cosine of theta plus 1, I'm going to go ahead and distribute that out at least. That's 6 cosine of theta plus 6. Sine squared we can replace by 1 minus cosine squared. And this is a little bit better because now everything is cosine, so I want to move it all over. I definitely want to add this to the other side to make the cosine positive. So that gives me cosine squared of theta plus 6 cosine of theta, and then subtracting the 1 gives you a 5. Okay. And again, you can make a u substitution here if you would like, but the more you do this, the easier it becomes to factor. To get cosine squared, you just need a cosine and a cosine. And then the only nice way to multiply to 5 is 5 and 1. And everything is positive, so we go ahead and make it all positive. The outer gives you 1 cosine of theta, the inner gives you 5 cosine, which indeed adds up to 6 cosine. Okay. So now this gives me two equations that I have to solve. So cosine of theta plus 5 is equal to 0, or cosine of theta plus 1 equals 0. Going through this first one, this would tell us cosine of theta equals -5. But if you think about the range of the cosine function, it's only a ratio between -1 and 1. So there are no theta values that solve this. So the only solutions I'm going to get are from the second equation where cosine of theta equals -1. And that is what we did before. The only angle that happens for is pi, but again, I want all possible solutions. So we add that multiple of 2 pi. and that n is just representing an integer. So those are my only solutions, but again, there is an infinite number of them, okay? This next one's definitely going to be the hardest type of problem. So if you need some more examples, just send me a message. I can find more videos on it for you. But it's going to be when we change that inside argument to something other than just theta. Okay? This is very time consuming for this, especially because I'm looking for specific intervals inside 0 and 2 pi. Okay? To begin with, though, I definitely hate dealing with cosecant. So instead, I'm going to turn this. This is the same thing as asking, where does sine of 3 theta over 2 equal the reciprocal, which is a half, okay? So I'm going to ignore the fact that I have an expression in here if I'm thinking about the angle that needs to be on the inside. For sine to equal a half, the inside has to be pi over 6 or 5 pi over 6. So there are 2 points on the unit circle. With an output of a half, we know that sine of pi over 6 will be a half. And then also back here, sine of 5 pi over 6 is a half, okay? So this occurs when the inside is pi over 6 or 5 pi over 6 or any multiple of 2 pi added to that. Okay. So it seems like we shouldn't worry about the plus 2 pi, but remember what this 3/2 does is it ultimately changes the period of the sine function. So it ends up speeding up how quickly we go through one revolution. So from 0 to 2 pi, there were originally only 2 values that made sine equal a half. But now with that sped up period from 0 to 2 pi, maybe you go around a few revolutions. And in that case, you then have a lot more options where sine is equal to a half, okay? So the way I like to go about this is I'm going to start with just this pi over 6 angle. If the inside is equal to pi over 6, then I have a solution, okay? Or if the inside is equal to pi over 6 plus 1 revolution, okay? Or if that inside is equal to pi over 6 plus 2 revolutions, which would be going around 4 pi. And then for good measure, we'll do one more. Go around a third revolution would mean we add 6 pi. And then again, really, you can keep going through this, okay? So if the inside is equal to this, 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 or this, the sine function will output a half. Okay? So I'm going to go ahead and condense what those things end up being. That is pi over 6. If you think about adding 2 pi, that's 12 pi over 6. So this would give you 13 pi over 6. So again, this is saying that sine of 13 pi over 6 is a half. Okay? And that's where you've gone an extra revolution around. When I add pi over 4, or add 4 pi, that would be 24 pi over 6. Adding 1 to that gives you 25 pi over 6. And then here, when I add 6 pi, that would be, let's see, 36 pi over 6. So adding one more, if that inside is 37 pi over 6, you have sine of theta equaling a half. But then that list again continues on. So instead of just writing it in this condensed form, all I've done is made it so that I've looked at the first couple, 1 revolution, 2 revolution, 3 revolution. But that's when the inside equals these. My goal is to figure out what theta equals. So I need to go through and solve this for theta. So I'm going to go ahead and I'm going to multiply everything by 2. So that gives me 3 theta. The nice thing is when you multiply all of these by 2, then all that's going to happen is 2 over 6 becomes a 3. So this is pi over 3, 13 pi over 3, 25 pi over 3, and 37 pi over 3. And then that list keeps going. So then to get theta, I need to get rid of that 3. So I'm going to times by a third. So that's going to change these denominators, if I times it by a third, to all be 9s. So if I plug in theta is pi over 9, it's going to work. 13 pi over 9 will work. 25 pi over 9 will work. And 37 pi over 9 will work. And then again, the list keeps going, okay? So just to show you this is true, again, I'm saying sine of 3 theta over 2. If I plug in pi over 9, that would be sine of 3 times pi over 9 over 2. Well, pi over 9 times 3 gives you pi over 3 divided by 2. That gives you sine of pi over 6, which indeed is a half. So that solves this equation, okay? So again, if I plugged in any of these, it would work and give us sine of an angle equaling a half. But I only want the angles between 0 and 2 pi. So I have to figure out, well, are any of these, or what number gets me out of that range? Because this list goes on and on forever. So really, you're just going to look at that fraction. If you take 13 and divide it by 9, 13 goes into 9 one time and then has a remainder of 4. So this is 1 point something. That's definitely in between 0 and 2 pi. If I look at 25 over 9, well, 25 divided by 9 would give me 2, and then I have a remainder of 7 over 9. So this is going to be more than 2 pi. I don't know exactly what it is, but I know it's 2 point something because 9 divides into 25 2 times. So really, immediately what that tells me is then any number after this is going to be no good because they just get bigger and bigger from going more revolutions around the unit circle. So really, I only end up with these 2 solutions for the pi over 6 angle, okay? So that gives me 2 values that work. Now I need to do the same thing for 5 pi over 6. So we need that inside argument to equal 5 pi over 6, or 1 revolution around, or another revolution around. You could do a third one, but really, once I hit that second revolution, it was useless, so no reason finding another one. So combining those, same directions. If I add 2 pi over 6, that's 12 pi over 6. So that gives me 17 pi over 6. Adding 4 pi would then be 24 pi. over 6. So adding 5 to that gives me 29 pi over 6. Okay. Then I just need to solve for theta, so same directions. I go ahead and I multiply by 2. That will get rid of this, and it turns all of the 6's into 3's. So we get 3 theta is 5 pi over 3, 17 pi over 3, 29 pi over 3, and then it keeps going. And then I've got to get rid of the 3, so I multiply by a third, cancels that out, and turns all of the 3's into 9. So we get 5 pi over 9, 17 pi over 9, 29 pi over 9, and then so on. Okay. So I have to figure out which ones work. And again, theta has to be in the interval from 0 to 2 pi. If you want to break that down into 9's, theta has to be between 0 and 18 pi over 9. So this one is less than 18 pi over 9, and so is this one. But then all of these will end up being bigger. Okay. So I really just end up with 4 angles that work in this interval. Pi over 9, 13 pi over 9, 5 pi over 9, and 17 pi over 9. So writing all those out, we got pi over 9, 13 pi over 9, 5 pi over 9, and 17 pi over 9. And then you can put them in order if you want, because the 13 and 5 technically should be switched, but not the end of the world. So those are 4 solutions to our equation. So just to show you with the graphing calculator what this is, if I go ahead and graph y equals sine, let's see if I can get that on here. If I type sine, it might work. There we go. We've got sine of 3 theta over 2. Okay. That is what our graph of the sine function looks like. And I want just from 0 to 2 pi. Pi, remember, is 3.14, so it's something between 0 and 6. I want to figure out where sine of 3x over 2 is a half. So if I also graph y equals a half, we can go ahead and see that between 0 and a little more than 6, there are 4 solutions. I've got one right here, which happens at pi over 9. A second one right here, 5 pi over 9. A third, and a fourth. So those are exactly the 4 solutions that we found analytically. So we're going to do 2 more examples. Again, if you need some extra work, there are tons of videos out here on this subject. It is an important one, so you can absolutely find stuff. Again, just search like trig equations with altered angles or something like that. For this next one, we've got cosine of 2 theta plus 6 sine squared of theta equals 3. My number didn't copy, okay? And so I run into an issue here. I have cosine of 2 theta, and then I also have a completely different trig function. So I want to rewrite this using the same trig function and that same argument. So this is where our formulas come into play. So we have a ton of different ways we can write cosine of 2 theta. Remember, we have 2 cosine squared minus 1. But to get everything in terms of sine squared, the formula that works out a little bit better for us is 1 minus 2 sine squared of theta. So when I go to solve this equation, instead of using cosine of 2 theta, I can replace it by 1 minus 2 sine squared. And then I can condense. I've got -2 sine squared and 6 more. Oh, iPad's going a little crazy. So that gives me +4 sine squared of theta. And then this is nice because I don't have a sine and a sine squared. I just have sine squared. So this is just like solving 1 + 4u squared equals 3. So I can isolate u and take a square root. So in this case, I'll move that 1 to the other side. This gives us 4 sine squared of theta equals 2. Dividing by 4 gives us 2/4, which is a half. And then taking a square root and remembering my plus or minus gives me plus or minus the square root of 1/2. But I better be able to find nice angles, and I don't know this one right off the top of its head. So this is the same thing as plus or minus 1/√2. And then rationalizing that denominator, that's √2/2. Okay. So I'm ultimately looking for two equations. I'm trying to figure out where does sine of theta equal positive √2/2. And then where does sine of theta equal negative √2/2. And thankfully these, I just have a theta argument. I don't have to do anything fancy. I am looking just for the values between 0 and 2 pi. These are my 45-degree angles. So sine of theta is positive √2/2 in quadrant 1, which would happen at pi/4. And then quadrant 2, which is 3 pi/4. So those two are solutions. And then over here, to get negative, that would be quadrant 3 and quadrant 4 with that 45-degree reference angle. So that's 5 pi/4 and 7 pi/4. Okay, so those are the 4 solutions. For this very last one, it's a little bit different. I'm not solving equations whatsoever. Instead, I want to solve this equation for x. It makes these restrictions just on the x value, just so things work out. It's kind of like when we were going through and rewriting inverse trig functions evaluated at something else and vice versa. We're just making restrictions so things work out nicely. But here I just want to get x by itself. So first thing I need to do is I need to get rid of that 1/5. So I'm going to go ahead and multiply everything by 5. That gives me 5y equals sine of 2x. And then I need to get rid of this sine function. And so the only way I can cancel that out is using my arc sine. So really at this stage, I want to take arc sine of each side. So this is a little weird to write. I don't want to write it just like that, but that's the idea. I'm going to take arc sine of each side because if 5 equals 5, arc sine of 5 is arc sine of 5. It's the same thing. Okay. So really this gives me arc sine of 5y will equal arc sine of sine of 2x. And because these two are inverse functions, they're going to cancel out. That's where these domain restrictions happen to make sure it does. Okay. So this gives me arc sine of 5y equals that inside argument, which is 2x. So just dividing by 2 solves for x. X is 1/2 arc sine of 5y. Okay. So again, these are just a sample of different types of problems. You're going to have other variations of them. You might need to use some trig formulas you've used before, but there's not one set approach for these. Okay, so try your best. And again, if you need more videos, just reach out.